of the recent advances in this new field, especially, I mean, with the recent growth of AI machine learning techniques that open doors actually for many adaptation that could be possible, especially with the large scale of software that we are dealing with nowadays in industry. So basically, my talk will cover several aspects of software engineering intelligence with some concrete case studies, and I'll be also making some live demos of how this technologies actually could work in practice to solve some large-scale software problems, mainly related to the improvement of the quality of software systems, architectures, and so on, and basically how you can combine different intelligent methods together in order to solve some challenging problems. So of course, probably many of you are probably familiar with the area of search-based software engineering, but what I'll be talking about today is probably beyond search-based software engineering, where search-based software engineering is limited to the use of computational search, mainly meta-heuristic search to solve software engineering problems. But after working on this field for many years, so we actually come to the conclusion that most of recent practical problem require actually combining different of this intelligent method like NLP and so on in order to solve this problem. But before going into that, so let me start probably with a brief overview about the motivations of this field and how could come naturally from the way how actually software engineers try to solve problems in general. Because scientists in general, the way how they think about problems in general is mainly to make things perfect, trying to prove correctness. But software engineers in practice, they try to think about how can I probably have an acceptable solution now to test my system, probably to have an acceptable improvement of quality before releasing my code. But in general, it could be less, I would say, formal sometimes, especially with all the pressure, all the problems that we could deal with, like pressure on releasing your code and so on, that could, I mean, put a lot of pressure on the budget and so on. So of course, I mean, whenever you can prove correctness, you can probably, for example, ensure 100% coverage of your code when you test it, when you can target optimal quality, that's perfect. I mean, you can do it within your available resources, but most of the time we deal with really very constrained environment where we are looking for probably not really the perfect solution for your problem, but something that could work for now, and then you can try to improve later. So this is kind of one of the main motivations around looking to different software engineering problem as either search problems or intelligent search problem for solutions that could be probably really imperfect, but they can be actually improved over time. So I want to summarize here kind of the 5 main dimensions around what could be the motivations for this field. Like you can use this probably 5 dimensions to motivate the use of intelligent methods in addressing software engineering problem whenever you think that your problem actually require to be classified in one of these dimensions. So the first one is the need to make predictions. So as you know, there are a lot of work around predicting bugs, predicting quality, predicting changes in order to better manage resources and so on. So that could be one of the natural motivation in general is actually you have to address problem where you have to deal with prediction in general. The second problem that you may deal with, especially with many software engineering projects and problems that could be related to searching in a very large search space, like especially with the current size of software systems, sometimes you don't have enough constraint to reduce the search space for your solution. Like, for example, when you look for generating test cases, when you look for program repair solution, sometimes you have to look into, I mean, very large search space that include so many code elements that or model elements that you need to deal with in general. And exploring this very large search space sometimes require the use of meta-heuristic search combined with several other ML algorithms. The third motivation in general, it's very important, especially when you deal with validation in the real world, is how you can actually find a trade-off between different conflicting objectives. Example of trade-off could be, okay, I want to improve the quality of my code or models, but at the same time, I want to actually meet deadlines, or I want to reduce the effort, or how can I generate test cases that can maximize coverage, but at the same time minimize the number of test cases to execute. And even when we deal with the same problem, like even if you take some long-standing problem like software quality in general, where you want to detect quality issues, you try to prioritize them, fix them. Actually, this field, for example, is based on the use of many quality metrics that are naturally conflicting. Like if you take coupling, cohesion, number of lines of code, and so on, all of these metrics are actually conflicting to each other. When you try to improve one metrics by modifying your code or your architecture, so you are actually deteriorating the others. So like coupling and cohesion. So how can I find a method that can, and adapting it in order to show the possible trade-off, and based on my context I can adopt actually the solution that I want. So if I have enough resources, like enough available people to improve my code, I will not really care about the effort related to that. I will just select the solution that improve as much as possible my code. In another context, I have limited time, so I may have select another solution. So finding this diverse set of solution is something that could be enabled through intelligent method like multi-objective search, and I will show you that during some live demos on some industry projects. And the fourth main, I mean, motivation is also scalability. So although we can solve many problems, actually at the small scale, but when we target large scale, like some of the experiments that I'll be showing later were done at eBay, where, I mean, we are dealing with more than 1.2 billion of calls between services. So this is could be really, I mean, coming very large. Like during this experiments, we experienced it per day, 1.3 trillion calls between services at the back end of eBay.com. So how to deal with improving the quality of the services and so on. So when you think about the large scale, this is when the problems becoming more exciting, more challenging, and at the same time motivates looking for some suboptimal solutions for your problem. And the final motivation in general, probably to motivate the use of this intelligent method for many software engineering problems, is how you can actually learn from data, because many of the recent trends now, as I will show you later in some case studies, actually, for example, based on how you can combine intelligent methods with the interaction with the user, because looking for completely fully automated solution could be very challenging for several problems, and you need to have user feedback. But how we can reduce the effort of interaction with the user. So the user can give you feedback to your tool, but how you can actually learn from this feedback to make your tool more intelligent and avoid giving the same recommendation and the same level of feedback. So learning from interaction is actually one of the main, I mean, challenges, and but at the same time benefits actually of combining ML with other traditional software engineering solutions. So So I would think, I mean, based on the recent trends and the new advances in the AI field, so this field is actually very well expanded nowadays, and this has opened doors to so many exciting applications in software engineering, model transformation, detection of defects, predicting bug, cybersecurity, and nowadays, I mean, with the recent trends in AI like deep learning, reinforcement learning, multi-object optimization, and so on, there are so many actually exciting potential, probably I would say, intersection between the two fields that can enable new exciting solutions and addressing long-standing problems in software engineering from a different view. So after showing all this motivation, the goal here is to try to kind of find a way to define this field of software engineering intelligence. And one of the definitions that I would propose, it's based on a combination of learning, search, clustering, and NLP techniques to find relevant problem in the context within a minimum interaction effort. And here I want to explain why we may need to combine all of these techniques together. And also I want to emphasize the word relevance, because relevance is different than correctness. So you can have a correct solution, but whether this correct solution is relevant or not for your context, this is another problem, because you can find the correct solution, but you cannot apply it within your context because it could be time consuming to change the code based on this correct solution. So you may look for a relevant solution where you probably have probably lower improvement of quality or less coverage, but it actually fit in your context. So actually that's, I mean, one of the main motivations of this field is how you can dynamically adjust your solutions within the context, within the user developers preferences, and finding trade-offs, and even trying to unify tasks together. Because as you know, with the uh, recent trends in DevOps and so on, many of the tasks like regression testing, refactoring, code transformation, adding new features, scheduling, all of these tasks may need sometimes to be unified in a way that we can actually consider any of the changes in different tasks of the life cycle and their impact on other tasks. And there are recent trends in AI and machine learning, like multitasking optimization and so on, where you can actually combine all of these tasks together. And another also important aspect within this field is the explanation of the results. So that's actually a very important aspect. I remember when I started working on the field of refactoring, probably 11 or 12 years ago, with several collaborators, one of the main challenge was that not only we were trying to find correct recommendation to fix your code, but also explaining them to the developer was actually the biggest challenge, to convince them to apply this code changes. So explainability is a very important aspect, and here there are a lot of work in this space of explainable AI, where there are a combination of decision trees with a regular learning algorithms as well to explain your results and why this is a good solution, what patterns exist, and so on. And another important aspect and areas within this field is about these intelligent bots that can be integrated, for example, in continuous integration environment, including GitHub. And I'll be making a demo of one of our intelligent bots for making code changes to improve quality, that it can go ahead and submit pull requests to be reviewed by programmers and monitoring your GitHub repo and so on. And this is based in the back end on a combination of all these methods together. So So to summarize, I mean, to define this field is kind of a combination of different areas, including search-based optimization, machine learning clustering, natural language processing, especially for problems related to automated documentation and so on. And there are so many problems in software engineering that could fit within all of this potential solution. So one of the main differences between software engineering intelligence in general and conventional solutions in software engineering, that here, the way how we think in general within the software intelligence field is how you can combine these methods to know which solution is better than the other and trying to provide explanation why, rather than trying to construct and write a method to actually find the perfect solution. And that's involved, as we discussed, in finding trade-off and so on, as I will show you later based on some live demos. So one of the advantages of this field is to deal with the subjectivity of many problems in software engineering, like when you are trying to improve design. This is really a very subjective problem. It depends on your preference as a developer in general, and also you have to deal with different conflicting constraints. So how you can find diverse set of solutions that could fit again with your context and so on. So probably some of you may say, okay, this machine learning AI methods were probably applied for so many problems in engineering in general. So what makes probably software engineering different and probably one of the best uh, applications or adaptation comparing to other engineering field could be done within our field. So if we take how this methods, this intelligent methods actually use it in other engineering fields, like electronic engineering and others. So in general, they try to run this intelligent methods on a simulation or a model that represent the real system. So they try to define whatever optimization goals and running the algorithm on a representation of the real system. But one of the advantages in software engineering that your engineering material is actually the model or the code that you can actually take actions and apply your solution directly on your system, on your software system, and then trying to evaluate the impact of the solution. And you get kind of a more realistic and also accurate estimation of the impact of those solutions and so on. So I think one of the main difference between trying to use intelligent methods in other engineering field comparing to software engineering is this ability of applying your potential solution, for example, during the optimization process on the real engineering material, comparing to what happened in other fields that they apply it on a model that represents the real system. And then when you try to apply the solution on the real system, the results could be even different due to the fault tolerance and so on. So this field is growing very fast and so on, and there are so many applications and also recent trends on combining all of these intelligent methods to address really interesting problem. And this is could fit again with how software engineers, they try to look to problems. So if you hear software engineers about, when they talk about this problem, they talk about satisfying business and technical constraints. They want to reduce risk while meeting deadlines. They want to increase cohesion, reducing coupling. They need to reduce test cases, and at the same time maximizing coverage. They want to optimize many metrics, and that's cover different part of the software life cycle in general, and that's make the applications actually pretty large. So to summarize, several benefits could actually achieve it by adopting these methods, including scalability, finding realistic solutions that deal with conflicting goals, robustness, how you can actually find a solution that will be that could be dynamically adjusted based on the change in your, for example, environment like code, model or change in the requirements or the priorities. So there are a whole, set of solutions around robust optimization that could be actually used in order to generate this kind of solution that are not very sensitive to the dynamic changes and the highly changing software engineering environments in general. And then another advantage of using this intelligent methods in general is that you can use them in a generic way where there are kind of common steps to follow in order to adapt them to your problem, as I will show in the next slides for the different case studies. So one of the case studies that I'll be focused on is around software refactoring. So probably many of you are familiar with refactoring, where the goal is to try to restructure your goal, your architecture, your model, while trying to preserve the behavior. And this is, a long-standing problem within the software engineering field, and it's basically defined by Martin Fowler in '99 as kind of trying to improve this internal structure while trying to preserve the behavior. And refactoring is now very well integrated to be applied manually in different integrated development environment. Like you can apply extract class to actually take part of the class and method and create them in a different class, or moving methods, and all the kind of restructuring that you can do in general in order to fix some large classes in your code, like to reduce the coupling in your code and so on. And if you want to actually learn more about this field and what exists and so on, I encourage you to visit our very recent established refactoring repository, and they have a paper also associated with this that summarized like 30 years of refactoring research in this field. So if you go to refactor, not refactor, is slr.iclab.us, you'll find actually a dashboard for all existing research in the field of refactoring in general. But I'm not here talking about just code refactoring. I'm talking about model refactoring and so on. And one of the surprising results when we collected all these papers of 30 years of research in the field, you can see like model refactoring, for instance, is becoming kind of very common and almost having the same level of work that is done with code refactoring and so on. And you have different criteria to select the works that you want to focus on based on the objectives, like improving quality or security and so on. You can see that this field is actually growing very fast in the last year, and you can see the distribution of the work and the active researchers in this field and so on. And you can also look for all the publications within that field, and just searching for whatever publication within the field of refactoring based on different criteria, like you want to focus on code refactoring, architecture refactoring, model refactoring, database refactoring, or probably the life cycle, whether detecting refactoring opportunities or testing or programming languages. And also you can find all the list of thousands of authors who contributed to this field. In general, over 5,000 authors contributed to the field of refactoring during the last 30 years. So you can find, whatever you need to quickly get access to this field. So we have been working this field of refactoring during the last at least 12 years. And one of the exciting experiences that they had was through the NSF I-Core grant, where we basically spent a lot of time, at least 2 years, talking to many companies and developers, managers, and executives of so many companies to understand the challenges within this field and why existing tools and refactoring that are not actually widely used in practice, except, for example, doing manual refactoring, but automating this is a big challenge. And we found that that they mentioned a lot of problems, including a lot of customization effort are required to use these tools that can automate refactoring. So they're looking for more intelligent method that can learn from their preferences and so on. And also, they don't see a lot of visualization support to understand the impact, the benefits of this refactoring to improve the quality of your code. So there was kind of a consensus that most of the challenges are more around how you can make your um, refactoring tool dealing with more constrained environment where programmers, they just want to spend less effort on doing refactoring, but they want to kind of prioritize fixing the most important issues. And this is, I mean, a big problem in practice because most of software engineers who join, industry, they want to work on um, implementing new features, on basically changing the world by, improving the existing tools rather than spending a lot of time and boring probably time on trying to restructure the code that could be actually painful, especially in very large system that has been there for over 20 years and trying to understand the code that has been written by author and trying by others and trying to fix it and so on. So this could be a very painful process, but at the same time, the consequence of that could be actually huge. And let me share with you one of our recent killer experiments with one of our industry partners, eBay, to appreciate probably how big is this problem that could be in industry. So in eBay, they have more than 10,000 apps and web services running almost daily at the back end of ebay.com. And they found actually, and we collaborate with them and we did some studies at the beginning to understand how big is the problem. And we found that any query on the website actually could generate at least the execution of 70 web services in the back end just for one request. When you go to the website and you try to launch a query in order to find specific products, that could be actually time consuming at the back end. And we found that the reason of that is actually related a lot to the existence of clones in the services where the same services are duplicated, and actually a huge coupling that is going on because of this dead services that are still there on the system that's increased the path in order to find the right information in the correct database. And that generates actually more than 1.2 trillion transaction per day to the database. And that's like basically cost the company over $50 million just to actually pay and maintain this transaction. So this is, you can see how could be large and big the problem of technical debt in general when people, they try to add new web services, new code without actually really looking to the whole architecture and how they can actually maintain it in a timely fashion rather than keeping things accumulating until that it becomes very costly for the company. So there are several, tools that has been proposed within the field of refactoring, improving code and architectures in terms of quality, security, and so on. So I would probably put them mainly on two categories. The first one is mainly manual support. They provide refactoring operations like extracting a method, class, and so on, but you have to actually manually detect where to apply these changes and why you are applying them. So they provide many support to execute this refactoring, and like what you have seen on Eclipse and many other integrated development environment. But also there are tools that are, I would say, underutilized that try to fully automate the whole process, which could not be realistic for the context of programmers in practice because they may not trust your tool that can go ahead and modify their code. It lacks flexibility because, we have seen in practice that programmers, they always ask for the possibility to customize, for example, the rules that you are using to detect these quality issues. They don't actually want to see hundreds of quality issues that you are generating, at each execution of the tool, like SonarQube and many other tools. But they want to actually customize um, what they actually want to target in terms of quality issues, and also looking for actual code changes that they can review. And one of the main challenges that they face it with existing automated tools, that in general they provide a very long list of static refactorings that they have to be applied, and whenever they reject one recommendation of code changes, it makes the whole sequence actually not adequate to apply. So there are a lot of customization, and also lack of flexibility in this tool that make them in general underutilize it in practice. So here is why probably the use of intelligent methods could be actually adequate for addressing the refactoring problem. First of all, when we deal with refactoring, improving quality, you have to deal with so many conflicting objectives that are your quality metrics. So how you can probably deal with this trade-off that you need to target in order to deal with all these conflicting metrics. The second thing is also the robustness, because people are making changes in parallel in your code, how you can dynamically adjust your refactoring recommendation, how you can enable interaction with developer by rejecting, modifying, deleting some of this recommendation, and how you can learn from that and provide scalable solutions, and so on. So that's fit with all the actually 5 dimensions that we were discussing about predicting quality changes, about searching in very large code bases, and about finding trade-off between metrics, about learning from interactions with the user. So that's all feed with actually the use and motivate actually the use of a combination of intelligent methods. And we have been working in this field for so long, for refactoring code, refactoring web services, refactoring model transformation, and so on. And we finally ended up by combining all of these methods together, including NLP, intelligent search like multi-object optimization, neural networks, and so on, in order to actually provide kind of an interactive optimization support for programmers in practice. And the question that was guiding us is how you can actually find the minimum recommendation guidance that could actually lead automated search to provide realistic recommendation that could be adjusted based on interaction with programmers. So for that, we try to combine different methods, including machine learning and multi-object optimization, while enabling interaction with the user to build a framework where you can actually enable all this interaction with an automated algorithm that can try to optimize multiple quality objectives that could be related to quality, security, and so on. And then you generate recommendations, then you have interactions with the user who can apply, modify, reject your recommendation. And then based on that, you can actually improve your search for what could be better recommendation that you can provide in the to the user. Like, for example, you notice that the user is rejecting any code changes that you are recommending to a specific method. So your search algorithm need to learn automatically this kind of constraint, and trying to dynamically adjust the search, for example, to avoid having in your solution code changes that target specific methods. So this is some example of simplified learning out of this interaction, but this learning could be much more complex, especially how you can actually identify a subsequence, or I would say a graph of dependent refactoring that need to be recommended together, comparing to looking to isolated refactoring. And also we did works based on the use of decision trees as well, to learn from very large repos of refactoring of what will be in general the preferences of the programmers, whether by identifying the relevant files that they in general try to refactor, or how they actually deal with these issues in general, and trying to feed the search algorithm in order to find better solutions in general. So we try to look at this whole loop of how we can combine all of these methods together. And one possible adaptation, as I said, could be done in a generic way, which is by answering these three main questions when you are trying to adapt any intelligent method in general for your problem in software engineering, is how to represent your solution, how to evaluate the quality of solution once you are able to generate it, and how you can generate new solutions based on what you learned in your fitness function execution. So if I take the problem of refactoring, so as you know, we have so many refactoring types, and you can support many of them to generate a vector of different refactorings that could be applied to your code, and then you can evaluate them using many fitness functions. And there are different quality models there that are defined, like reusability and understandability of your code, which is based on different low-level metrics. And then we adapted an NSGA2 algorithm to actually find the trade-off between all of these conflicting objectives together, where you can generate the set of non-dominated solution, where you can say that this solution is better than this one, because the first one is optimizing better this objective that could be, for example, increasing cohesion, while the other one is better in terms of coupling. Uh, so we can try to find all of this trade-off to the developers so that he can automatically and implicitly navigate with the solution. So I want to show you probably a demo of how we combine it, actually, all of this multi-objective search algorithm with clustering algorithms as well, in order to identify some relevant solution. If I go to our website, refactor.iclab.us, which is a publicly available platform, actually to refactor your project. So if you go there, so you can request an account and we can approve it for you. And you can see, like, we have here different categories of projects that we try to evaluate their quality, and even generating a total quality index to say how bad or how good is the quality of your project. So to use our platform, it's very simple. You can try to just specify, for example, the GitHub repo of your code, and then it will be added directly to our database via the GitHub API, and we can generate a whole report about the quality of your project in general. So generating, I mean, a whole report that's include checking the quality of your project and comparing it to a specific benchmark. Because when you say that the quality is bad or good, it depends basically on which benchmark you are using. You can select a benchmark like industry projects. Like here, we are comparing to eBay projects, for example, the quality of this project, which was graded B in total, and you can see which ones are actually lower than typical industry standards. For example, at eBay, like the cohesion, the coupling is lower than what we found in this industry projects, and then you can understand which quality metrics you may want to focus on comparing to the benchmark that you use it. And then we can give you detailed as well issues that were detected based on their location and so on, and we can tell you if they're critical or not from security perspective. And then we actually provide code actions based on your needs. So if you can see, probably the least um, quality metric here, you can see that probably effectiveness, and there is actually knowledge base to understand how we are calculating all of these quality metrics and so on. You can rank your proposed code changes based on effectiveness. And then you can get actually the list of code changes that are proposed in order to deal with that, like extracting classes and so on. And then you can see the code before and after. You can see the impact on quality improvement, because some metrics could be improved, some other not. And you can see the code before and after. And then if you accept this recommendation, that will generate a commit directly on your GitHub repo. So that's one example of how we actually combined all of these methods in order to build this platform to deal with these issues. But also we worked on integrating this as a bot, as an intelligent bot in your GitHub repo as a GitApp, where you can actually have it used in continuous integration. And we deploy this actually in big companies like eBay, and we learned a lot out of this. And you can find more details in our paper, like our ASC or our recent TSC paper around this. So here is also probably a final demo as well about how this was integrated in GitHub. So we actually built a GitHub where you can directly do the mentoring of your GitHub repo. We can tell you what quality issues basically exist, and also directly evaluating the quality of any of your recent pull requests, but also generating a pull request to fix the different quality issues that we observed, and you can review them as kind of a regular pull request that could be submitted by any programmer. And this is, for example, the pull request that was generated by the bot after detecting some quality issues in your recent commits. And also you can get explanation of why actually this code changes were provided, so you can actually get connected to our web app via your GitHub repo and understanding the changes before and after your last commits and why the changes are recommended. And then you can accept, reject some of them. And then, once you decide to integrate some of them, it will be directly accepted as a pull request that you can basically review like any other pull request. So thank you for your attention, and welcome for your question. I know that we are exactly within time now. Thank you.